Okay, today we'll start with the solution series of Bessel and Legendre's differential equation, especially ordinary differential equations. And today we'll start with ordinary differential equations for solution series. And this is also called power series method for solving ordinary differential equations. So the series solution, actually we'll try to consider this homogeneous differential equation because right hand side is 0. Here PQR is the function of x, and this is also polynomial in x, and PQR actually this is the second order differential equations whose right hand side is 0. So this is called homogeneous. If right hand side is not 0, then this will be inhomogeneous, non-homogeneous differential equation of second order. So we primarily consider the case PQR are the polynomial and hence also continuous. We'll consider this is the ordinary differential equations. And however, we will see the method of solution is also applicable when PQ are the general analytic function, actually differentiable function. Assume PQ are the polynomials with no common factors, and that we want to solve the equation below the neighborhood with the neighborhood of x naught. Actually, we're considering this as a neighborhood of x naught. Now this is the actually homogeneous differential equation of first order. So the point x naught is called the ordinary point where p of x naught must not equal to 0. So we can divide the whole equations on both sides with p. After dividing, we get this because p of x naught is not equal to 0. So small px is equal to what? Qx divided by p of x, and small qx equals to rx divided by p of x after dividing by p on both sides, especially. Okay. So this px is, if this px equals to 0 at x naught, okay, this will become the singular points. Understand? Okay, suppose this is the actually our ordinary differential equation. So if the p of x equals to 0, then it will be singular point. Okay, so pq are the polynomials with no common factors, and it follows that qx and rx not equal to 0 or both. Okay, so then at least small p and q r becomes unbounded as x is very near to x naught. Okay, so in order to solve these types of differential equations, actually ordinary differential equations at any point x naught in the neighborhood of x naught, we'll assume the series representation of the unknown solution yx equals to what will be summation n equals to 0 to infinity and x minus x naught to the power n. This we will consider the solution of this differential equation. Okay. And if this is the solution of this different ordinary differential equations, actually homogeneous differential equation, and it will be x naught at x naught in neighborhood. As long as we are within the interval of convergence, this is the representation of y is continuous and has derivatives of all orders because it is an analytic. Now, to find out the series solution of these types of differential equation, where p of x equals to 1, coefficient of y double dash, that means d square y dx square. Okay, this is the second order differential equation where p of x equals to 1, qx equals to 0 because dy dx coefficient 0 here, comparing with this differential equation. Okay, here px equals to and qx equal to 0 into this is why this absent in this equation, and rx equals to also 1, coefficient of y. Okay, so px equals, comparing with this standard ordinary differential equations, second order ordinary differential equations, we get p of x equals to 1, qx equals to 0, and rx equals to 1. Thus every point x is an ordinary point here. Now we'll take x naught equals to 0, assuming the series solution of the form y x equals to n equals to 0 to infinity and x to the power n, where x naught equals to what? 0. Now differentiating the term by term, we obtain yx equals to this. Okay, summation n equals to 0 to infinity and x to the power n, and y dash x means what? Y dash x means what? First differentiation. Okay, first differentiation of n equals to 1 to infinity and n into n x to the power n minus 1. Okay. Y double dash equals to what will be similar differentiation. Again, differentiation this on both sides. We get second derivatives and equals to 2, starting with 2 because x to the power n minus 2. Okay. And minus 2 equal to what will be 0. So n will start with what? 2. Remember it. Now substituting these two values, these three values, y first derivatives and second derivative values in the given differential equations. This is the second order differential equation. We get this only. Okay. Just y double dash equals to this and y equals to what? This is absent because this is absent because first derivative is absent here. Okay. Qx equals to what? 0. This is why. So substituting these values, we get this equation. Now our equation is this, n equals to 2, starting with 2, substituting n into n minus 1 and x to n minus 1. This is the second derivatives value and this is the y values. Okay, shifting indices we obtain. That means substituting n with n minus n plus 2. Okay, n equals to what? N plus 2. Then this n will become 0, n equals to 0 to infinity, and this n becomes n plus 2. And if we put n equals to n plus 1, n plus 2, then it will n plus 1. Okay, and if we put n equals to n plus 2, 2 will cancel, only xn. Okay, and these indices of a will become a n plus 2. Okay, and this is the same. Now take common. To take common, we have shifted indices actually. So n equals to 0 to infinity, we get n plus 2, n plus 1, n plus 2 plus this n, and then xn is the common here. Okay. I hope everybody is coming. Nizam, please tell them to join here in the class. Inbox them, please. So this is the shifting indices we obtain. N equals to 0 to infinity, n plus 2, n plus 1, n plus 1 plus n. Just taking common from this. This is the actually power series method or solution series method for solving what? Ordinary differential equations of second order. So after this, our equation is this actually this. Okay, this equals to 0. After taking common summation n equals to 0 to infinity and xn in right hand side, in right, this equals to 0. For the equation to be valid for all x, coefficient of each power of x must be 0, and hence that means coefficient of x to the power n. Okay, this is the coefficient of whole third bracket will be the coefficient of x to the power n. Coefficient what? N plus 2, n plus 1, n plus 2 plus n equals to 0. For this equation to be valid, x, this coefficient must be 0. Okay, because x is not equal to 0. Okay, because our desired solution is valid. To make a valid solution, we must take this as a 0. Okay, for individual and we get any individual and means, and starting with what? 0, 1, 2, 3 up to infinity. That will never finished. Okay, that will never finished. Or we can, n plus 2 equals to what? N equals, this equals to minus n. Okay, just alternating, then we get a minus n divided by n plus 2 into n plus 1, where n equals to 0, 1, 2, etc. Now these types of equation is called recurrence relation. Okay, this is called recurrence relation. For individual n, we can take different values of a. Next, we find the individual coefficient of a naught for n equals to 0, a1, a2, etc. Okay, suppose to find a2, a4, a6, that means odd, even power from this series. N plus 2 equals to what was? Minus n divided by n plus 2, n plus 1. Just putting n equals to 0, we get a2. Okay, this is the even. We get even indices of a. So for n equals to 0, we get this. For n equals to 1, we get n equals to 2, we get this. N equals to 4, we get this. Okay, we proceed in this follow. A2 equals to this. A2 equals to what will be? Minus n naught divided by 2 into 1. Just putting n equals to 0 here. And a4, just putting n equals to what? 2. Then you get 4 into 3. Then you get, this is actually, we can make a factorial. 4, 3, 2, 1. Okay, 4 into 3 can be written as 4 into 3 into 2 into 1. F4 equals to like this. So S6 equals to can be written as what? 6 into 5. 6 into 5. This. Okay, similar process. Now, if we take last k, we can make it a 2k equals to minus 1 to the power k as 0 divided by 2k factorial. Actually, this is the 2k factorial for k equals to starting with 1, 2, 3, etc. Now, odd coefficients to find out A3, A5, A7, we can proceed in this way. N equals to just putting 1. Okay, we get A3. N equals to putting 3, just odd coefficient. To get odd coefficient, we get 5, 4. Okay, and this is the 3, 2 and 5, 4. Then because 5, 4 here and A3 equals to what? A3 equals to this. This way, after putting A3, we get A1 divided by what? 5, 4, 3, 2, 1. Then A7 equals to what? Just N equals to 5. Putting here N equals to 5. Then A7 will be give minus A5 divided by 7, 5. But A5 equals to what? This whole. Okay. So A1 divided by 7, 6, starting with 5, 4, 3, 2, 1. So we can get for odd A, that means A2k plus 1 can be written as minus 1 to the, this minus 1 to the power k, A1 in every term A1 present. So this is the odd 2k plus 1 factorial or odd factorial. Okay, odd factorial for individual k equals to 1, 2, 3, etc. Now we know we now have the following information. Yx equals to, it was our trial solution, okay, of the differential equation. Where a 2k equals to this and a 2k plus 1 for if this is for even and this is for odd. So this solution can be written as Yx equals to what? A0 n equals to 0 to infinity minus 1 to the power twice n factorial for what? For this odd, and x to the power will be what? Twice n. And after, then second expression will be n equals to 0 to infinity a1 twice n plus 1. This is the actually solution, and this is the series solution by power series method, and we solved actually second order differential equations by series method. This is the actually solution. Okay, note that a0 and a1 are determined by the initial conditions. Okay, also by the ratio test we can show that these two series converges absolutely minus infinity to plus infinity, because they are here we used an natural number, it can never be finished, and this is why this absolutely convergent on minus infinity to plus infinity. So hence the manipulations we perform, the series at each steps are valid. So this is our actually solutions of that second order differential equations, homogeneous differential equations. For calculus, we know that the solution is equivalent to this yx equals to what? A0 cos x, a1 sin x. Just solving this, we can write m square plus 1 equals to what? 0. Constant coefficient method. Okay, constant coefficient method, m square plus 1 equals to what? 0. So m equals to what? Gives complex roots. Just previous class. In previous class, we have studied the linear differential equation with constant coefficients. We get the solution is this, what? A0 cos x plus a1 sin x. These are constant. You can take is as C1, C2 also. This will give only two constants. Understand? So, and this is valid for x lies between minus infinity to plus infinity. While we are familiar with the properties of cos x and sin x, many important functions are defined in the initial value problem that they solved. Actually, yx equals to this, we have solved this the ordinary differential equations by power series method. The graphs value with the partial sum approximation. Actually, this is the partial sum. Okay. So approximation of cos x and sin x. As the number of terms increases, okay, number of term increases, n equals to 4, 8, 12, 16, 20, we get this series. Okay, this is the actually cos series, and this is the actually what? Sin series, starting with 0 and starting with 1 will be cos series, and starting with 0 will be sin series. So this for what? Odd number. This is for odd number and this is for even number. N. And n equals to 2 is this, n equals to 6 is this, 10 equals to the 4 will be this, 8 will be this. So this is the whole are solutions of the differential equation. This is the solution, and this is the geometrical interpretation for even, and this is for odd. Remember it. So this is for individual n, we get minus values, and for n equals to another number we get positive values. Okay, this is why for we get in positive and negative values. Okay, so this is the geometrical interpretation of the solution of power series, solutions of the this power series. Okay, find a series solution of our equation about this x not equals to 0. Another types of second order differential equation where px equals to 1 and q equals to 0, rx equals to what? Minus x. This is the polynomial of x. Okay, thus every point x is an ordinary point. We will take x not equals to what? 0. X not equal to what? Will be 0. In similar process we can proceed, just same differentiation, same equation, just here extra x added, x to the power n plus 1. Okay, just x to the power n into x what? X to the power n plus 1. This is the just difference. Now taking n equals to n plus 2 here, we get taking n equals to n plus n into n minus 1, this taking n equal to n plus 2. Similar process we get this. Okay, so our equation is this actually. For this equation to be valid for all x, the coefficient of x, each power of x must be 0. Coefficient will be must be 0 as before example. So for n plus 2 equals to this for individual n equals to 1, 2, 3, etc. dot infinity. And n plus 3 also for, we can take this for odd indices. Okay, n plus 3 equals to this, n equals to n equals to n plus 1. Now we have a2 equals to 0, n plus 3 equals to this. For the recurrence relation, a2, a5, a8, all these will be 0. Next we find the coefficient as a0, a3, a6. So we do this by finding formula a3n, n equals to 0, 2 will give what? 6, 1 will give a3, in this way. This is the recurrence relations. So after finding that, we find a1, a4, a7 from the formula an plus 3. Just putting n equals to 1, 2, 3, etc. Okay, if n equals to 1, then it will be what? A4. Okay, if n equals to 0, it will be a1. If n equals to 2, it will be a7. Okay, very easy. Finding a3, a6, a9, etc. from that relation, we get this as previous example. The general formula for the sequence will be a3 and will be this. This is the actually factorial 2, 3, 5, 6. So for a4, a7, a10, etc., we get from this relation. The general formula will be for odd, will be this. Now this was the actually solution of our differential equations of the second order, and this is the indices for a3n, and this is the for even, and this is for odd. So this solution can be written as like this: power series for individual a0, n equals to 1, n equals to 0, then y0 equals to 1, y first differentiation will be what? 0. And this also, the for individual value of a0, a1, we get these values for if x equals to 0, y equals to the 1. Okay. Now the corresponding solutions y1, y2 are linearly independent since Wronskian. This is called actually Wronskian for y1 and y2. 0 equals to 1. Where Wronskian of 0 equal to what? In previous lecture we have studied about Wronskian. Okay, y1 0, y2 0, and this is the first derivative of y1 and y2. First row will be just function, and second row will be the first derivative, just taking determinant cross multiplication. Okay, so our solution was this for the cases we get first differentiation. This is the initial value problem. The corresponding solutions y1, y2 are linearly independent. And thus the fundamental solutions of the Ayres equation with the general equation. We can write yx equals to c1 y1x and c1 y2x, because the values are repeated roots. And we can represent this solution in a graph for first solution. This is the for the first roots, and this is for the second roots. This is the geometrical interpretation for n equals to odd and for n equals to even. This, okay. This is for n equals to odd y1 function, and this is for the y2 function. Okay, now we'll try to understand about the Bessel function, actually Bessel differential equation. Bessel function. Okay, Bessel equation. This is the differential equation of x square d square y dx square plus x into dy dx plus x square minus n square into y equals to 0. This is the actually Bessel equation. Okay, Bessel differential equation. And particular solution of this equation are called Bessel function of order n. The solution of this differential equation is called what? Bessel function of order n. And here n equals to what? N. There are this n indicate the order of n for Bessel function. Remember it, not for differential equation. This is actually a second order differential equation. But if we represent this solution as a Bessel function, then that will be in order of what? N. We find Bessel equation while solving Laplace equation in polar coordinates by method of separation of variables. This equation has a number of applications in engineering. There are about 9 applications Bessel function are involved in. The solution of this differential equation is called Bessel function of order n. Remember it. So this has 9 applications about here. The oscillatory motion of hanging chain, Euler theory of circular membrane, the studies of planetary motion, okay, in universe, planetary motion, the propagation of waves. Actually, we are using the waves. You are hearing my words, and we are hearing your words. This is the actually propagation of waves creating here. The elasticity in physics, the fluid motion, okay, fluid motion, the motion of liquid, okay, oil, the motion of oil, just transferring oil from one country to other country to collect oil. This is they indicate a motion for fluid. Okay, so this fluid motion to analysis we are using Bessel function. Potential theory, the cylindrical and spherical waves. There are different types of waves. Another is cylindrical and other is spherical waves. Theory of plane waves. Okay, Bessel functions are also known as cylindrical and spherical function. Remember it. Okay, so there are different types of solutions for this. Actually, Bessel functions, there are different types of different applications. Three important categories: waves in a cylindrical waveguide, heat conduction, electronics and signal processing. Okay, electronics and signal processing. Modes of vibration of an artificial membrane, acoustics. Okay, this is actually using in robotics. Electronics and signal processing, this is in field inside an X band cylindrical object, heat conduction. In a cylindrical object, we also use what? Bessel function. Heat flow initiated within a hollow infinite cylinder at an initial condition can be generated from the roots of the type of Bessel function. There are more and more. Application in electronic and signal processing, Bessel filter, Kaiser window, FM synthesis. This is actually in engineering application. I'm just showing you the where the application of Bessel differential equation, especially differential equation. This is the fourth order Bessel filter. Okay, SIM. This is the actually SIM 965 Bessel and Butterworth filter. Okay, this is the electronic machineries. How is it related to Bessel function? Okay, low pass filter is characterized by transfer function, also called network function. Its rational function denominator is a reverse Bessel polynomial. Huge application here actually. Okay. Kaiser window function, mathematical function, zero valued outside some interval. Kaiser window actually in engineering used digital signal processing. Okay, how it is related to Bessel function? This is the window function. And this is the geometrical interpretation of window function. FM synthesis. Okay, frequency modulation synthesis. FM synthesis means what? Frequency modulation synthesis. A format of audio synthesis. Actually, audio and video will come to us in what waveform. Okay, so this results in complex waveform and different tones are created for that. This is the actually we use Bessel function here. Okay, application in acoustics such as drum or other membrane phone. So this is the modes of vibration of a thin circular artificial membrane. Okay, first three Bessel functions are very important for this. A 2D wave equation to analyze 2D wave equation has Bessel function solution. This is microtensioned randomly arranged cylindrical membrane. And you must know about this. This is actually used for acoustics in the stage of a drama or for a singer. This is also Bessel function. How are you using? We are actually this is the actually using where. So other application include diffusion problem in a lattice, solution of the radial Schrodinger equation in a spherical and cylindrical coordinates for a free particle. Okay, there are many applications of Bessel functions, also Legendre functions. Okay, now solutions of Bessel equation we will use here power series method. Okay, in previous class, in previous example, we used this power series method. Okay, consider y equals to what? R equals to 0 to infinity AR x to the power m plus r. This is the actually we consider the dependent variable y. This is the solution of this differential equation. Okay, so y equals to what? Actually we can represent it as a series a naught putting r equals to 0 to infinity a0 xm a1 xm plus 1 a2. This is the series. Okay, so first differentiation what will be dy dx. Okay, first differentiation this will be what? Summation r equals to 0 to infinity ar x to the power m formula what? M plus r into x to the power m plus r minus 1. Okay, understand everybody? This is the first differentiation. Similarly, second differentiation d square y dx square summation r equals to 0 to infinity r m plus r x to the power n formula again. Okay, m plus r minus 1 into x to the m plus r minus 2, because x to the n formula what? N into x to the power n minus 1. Okay, now substituting these three values y equals to dy dx d square y dx square in the given Bessel differential equation, we get this. Just putting the values. Now taking summation r equals to 0 to infinity. Okay, r equals to 0 to infinity, just multiplying x square with this x to the minus 2 here. Okay, so x plus 2 again, So this will become only x to the power m plus r. Similarly, this is also m plus r, and this will become x multiplying this minus 1 will be cancelled. Only x to the power m plus r, and this will be also x square multiplying after we get what? This, and n square multiply this. So this whole term we can take common because x to the power m plus r are same here. Okay, just taking common we get x to the power m plus r, and this is the constant ar, x to the power m plus r plus 2. Now after taking common here m plus r, taking common m plus r will be m plus r whole square minus n square. Okay, m plus r whole square minus n square from this within third bracket. We get this. Now equating the coefficient of lowest degree term of x to the power m in the identity 3 is 0 by putting r equals to 0 in the first summation, we get the indicial equation. Actually we get it what? Putting r equals to 0. Putting r equals to 0, we get m square minus n square. X to the power what? M. So equate the coefficient of x to the power m. Just we have taken the coefficient of x to the power m. Understand everybody? For r equals to 0 also. Okay. So this will give m square equals to what? N square, because n not equals to not equal to 0. So m equals to n and m equals to minus n. There are two values of m. Now equating the coefficient of the next lowest term, x to the power m plus 1. After x to the power m, another term which one? X to the power m plus 1. So if we take r equals to 1, then we get a1 m plus 1. Just putting r equals to what? 1. R equals to 1. Then r equals to a1, and this will be the n square, and this will be the 0. Just equating on the coefficient on both sides. So we get a1 equals to 0, and this is not, since this is not equal to 0 because m is not 0. Now equating the coefficient of x to the power m plus r plus 2. Equating this coefficient. Okay. Equating this coefficient, we get ar plus 2 will be r equals to what? R plus 2. R equals to r plus 2. R equals to r plus 2. So m plus r plus 2 this will become. Okay, minus n square plus ar. Ar is this coefficient. So ar plus 2 equals to this, and therefore a3, a5, a7 will be 0. Okay, and since a1 equals to 0. Understand? If r equals to 0, a2 equals to what? This, and if r equals to 2, this will give. Just putting r equals to 0 here, r equals to 1 here. Okay, if r equals to 1 here, then a1 equals to what was? A1 equals to 0. This is why all these terms are 0, since a1 equals to 0. So we get a2, a4, etc. values and so on. So on substituting these values of the coefficient a1, a2, a3, a4, etc. in equation 2. In equation where? 2. Why? This is the actually solution series. This is the actually solution of this differential equation. So we get y equals to this whole term. Just putting first a1, a2, a3, a4, etc. we get this. So y equals to this will be, after taking common a naught x to the power m, we get this third bracket. For m equals to n, if we put m equals to n, then we get this. M equals to n. N plus 2 whole square minus n square will be 4n plus 1. Now here n naught is an arbitrary constant. For m equals to minus n, this. So this y and this y are the solution of the Bessel differential equation. And this is very important for you. I hope everybody understand this. Now Bessel function z and x. Remember it, Bessel function can be represented by z and x. The Bessel equation is this. Remember x square d square y dx square plus x dy dx plus x square minus n square into y equals to 0. And the solution of this differential equation, y equals to this. Okay. Solution of this in series. This equals to can be written as a naught x to the power n r equals to 0 to infinity minus 1 to the power r x to the power twice r 2 to the power 2r r factorial and plus 1 and plus 2 dot dot nr. Actually, this can be represented as sum of this. Okay, where n naught is an arbitrary constant and it equals to 1 by 2 to the power n factorial and plus 1. Just this is the actually this z and x equals to what will be r equals to 0 to infinity minus 1 to the power r factorial and plus r factorial x by 2 to the power n plus twice r. This is the actually Bessel function. Okay, Bessel function. We have to remember this function. Okay, so if n equals to 0 here, n equals to 0, z0 equals to what will be summation minus 1 to the power r factorial whole square n equals to 0. Okay, r factorial whole square x by 2 only to r for n equals to 0 here. We get this. So z equal to 0 means what? 1 minus x square by 2 square. Just putting summation values. So x to the power 4, x to the power 6, this. For n equals to 1, and we can interpret these two, first Bessel function 0 z0x and second one z1x in this series. Okay, we can represent this series in a graph, geometrical interpretation of this. So remember this Bessel function. We have to remember, we have to use this function in different solving problem. So this is the Bessel function, remember it, for n equals to minus 1. Now show that the Bessel function n is an even function when n is even and is odd function when n is odd. Okay, this we know. This is the Bessel function. Then x equals to r equals to 0 to infinity minus 1 to the power r factorial gamma n plus r plus 1 x by 2 to the power n plus twice r. This is the Bessel function, equation 1. Now replacing x by minus x, we get the same. Just replacing x by minus x. Now for the case n is even, that means n plus twice r is even. Okay, these are the same. Okay, for even, then this becomes same Bessel function. For n is odd, n plus twice r is odd, then if this is odd, minus will be outside. Okay, negative, this will be negative values for odd. So this is also negative, and this is Bessel function also negative. Odd function, from the definition of odd function, we get f of minus x equals to what? Minus f of x. From the definition of even function, f of minus x equals to what was? F of x. This is why the theorem is valid. Okay, this is important for you. Bessel function of the second kind, we'll know at our beyond the syllabus. Now example 3, prove that z minus nx equals to minus 1 to the power n z nx where n is a positive integer. Okay, n equals to what? Positive integer. And we know for n equals to minus n, this is the Bessel function. Okay, so this can be written as r factorial, and this is the what? R minus n plus 1 gamma. This is the gamma function. Remember it. This is the gamma function. So this can be written as r equals to 0 to n minus 1, then r equals to n to infinity. Okay, for n minus 1 odd, since negative integer equals to what? Infinity. This is why this whole will be 0. So this will be exist. Now on putting r equals to n plus k in this expression, we get this. And this is equals to x. This is actually Bessel function. Now very important example, z half x equals to square root over 2 by pi x sin x, and z minus half x equals to square root over 2 divided by pi x into cos x. We have to prove this. We know that Bessel function z and x equals to what? This. We have to remember this function, x to the power n divided by 2 to the power n gamma n plus 1. This is the gamma n plus 1. Break 1 minus x square by 2 into 2 n plus 1 plus x4. This is the gamma function. This is the Bessel function. Okay, now substituting n equals to half here, putting n equals to half, just x to the power half, 2 to the power half, and it will be half plus 1. Half plus 1 means what? Gamma 3 by 2. Just taking sum. Now we, from this series, we can write 1 minus x square by this will be 3 by 2. 2 will be cancelled, so 2 3 only. And here 2 by 3, and this is 5 by 3. So we get only x4 divided by 2 3 4 5 dot dot infinity. Okay, this is root x divided by root 2. Gamma 3 by 2 means what? Half into gamma half. Okay, half into what? Gamma half, you must know from integral calculus. I have shown you what about gamma function and beta function. So gamma 3 by 2 can be written as half into gamma half. Okay. So we can take 1 minus x, giving x in every term. Okay. 1 by x, and we have given x in every term. Okay. X into, this will be x cube and x5 dot dot. Every term multiplied with x, because we have taken common 1 by x. So after this series, 1 by root over twice x, half gamma half. Gamma half equals to what? Root 5. Okay, remember it. And this is the sine series actually. This is what? Sine series, sine x. So this can be written as 2 divided by pi x sine x, where gamma half equals to root 5. So we have proved the series. Again, if n equals to minus half, similar case, we get another series. Understand?
Yes, sir.
Okay. So that this square root over half pi x z 3 by 2. This we have to show this. Similar process, putting z equals to what? 3 by 2, n equals to 3 by 2 in the Bessel function. We know this from the solution, power series solution. This is the Bessel function formula, and putting n equals to 3 by 2 here. Okay, very important for you. Z 3 by 2 x. Just putting n equals to 3 by 2, we get this. Okay, putting n equals to 3 by 2. This is gamma 3 by 2 plus 1. Gamma 3 by 2 plus 1 means what? 5 by 2. Gamma 5 by 2 means what? 3 by 2 half gamma half. Gamma half means what? Root 5. And 2 to the power 3 by 2 can be written as 2 root 2. Okay. So this can be written as, now multiplying x square on both, in every term. Multiplying x square in every term and taking x square here. Okay. 1 by x square here. Okay. 1 by x square multiplied, then x square giving in every term. So we can write this is x square by, and this is what? 5 by 2. Okay. 5 by 2, 2 will be cancelled. So 2 5, 2 into 5. And here 5 by 2, 7 by 2. Okay. So 2 2 will be cancelled. So 2 4 5 7 only. And we get from this series root over 2 by pi x, and this is x square by factorial 2. Factorial 2 higher, just giving 2 in numerator of every term, denominator in every term, multiplying with half in every term. There are this half used. Okay. So x square by factorial 2 minus x square by factorial 3 plus x4 by factorial 5, we get this series. And this series can be divided into two parts. Okay. To root over 2 by pi x, third bracket 1 by x, second bracket x minus x cube by factorial 3. Just taking odd one, we get another series, and taking even term, we get another series. Okay. Understand? Equals to root over 2 by 2 divided by pi x, we get this is the sin x by x. This is the sin x series, and this is the what? Cos x series. Understand, everybody? This is the sin x by x, and this is cos x. So z 3 by 2 x equals to this. So this is the proof. Similar process, putting z equals to minus 3 by 2, you can show this result. Can you do this? Can you do this? Hello? Example 6, just putting z n equals to minus 3 by 2. Okay. Similar process, you can prove this. Important example for you. This is the first, there are recurrence formula 1 2 3 4. This 4 is important for you. 1 2 3 4. Just using Bessel function. This is the Bessel function. Zn x equals to this. This is the series of Bessel function. R factorial 1 minus 1 to the power r. This is the gamma n plus r plus 1 x by 2 whole to the power n plus twice r. Now differentiating, we get first differentiation. This just differentiating with respect to x. All other constant. X to the power n formula, x to the n minus 1. Okay, n into x to the power n minus 1. Multiplying with the coefficient of x, right? Half. Then we get multiplying on both sides with x, we get this. Okay, there are two n plus twice and there are two terms, minus 1 to the power minus 1 divided by n into n plus twice r. Actually, this n into whole this is the first term, twice r into this the second term. Okay, understand everybody? N into whole, we have divided into two parts. N into whole, this is the first term, twice r into whole, second term. Okay, then we get this is also Bessel function Znx, and x into this is the series, and to r factorial can be written as r into r minus 1 factorial. Okay, r cancel, we get this. So this is substituting r minus 1 equals to s here, and we can write this. This is also Bessel function of n plus 1. Okay, Zn plus 1. This is the actual relation. So try it at home. 1, 2, 3. Same procedure, same way. Okay, you can prove that this example 7, Z 5 by 2, this. Okay, just putting n equals to what? 5 by 2 in Bessel function. Now express Z6 in terms of Z0 and Z1. This is, you'll try it at home. I am going to another function. Another function is Legendre function. Okay, Legendre. This is the Legendre differential equation of the form 1 minus x squared d square y dx square minus twice x dy dx plus n into n plus 1. Here, this is the difference. N into n plus 1 into y equals to 0 is the second order differential equation, and it is called Legendre differential equation. It's known as Legendre equation. The above equation can be written as also UV method. Differentiation of UV, you get this. So we can similar process, using similar process, we can solve this by series, power series method. This will be homework for you. I hope everybody can do this by solving Bessel differential equation. Actually, the polynomial p and x are the Legendre polynomial function, but in Bessel function we denoted it what? Z, capital Z. But in Legendre we will use what? We use P. Okay, and Pnx and Qns are the two independent solution of Legendre equation. Therefore, the general solution can be written as A into Pnx plus B into Qnx, where Pnx is the and Qns is the, this is the series from solution, series solution, you get this, and Pnx is the function, this is the also series. Okay, Pnx, and combinedly these two series will give the general solution for the Legendre equation. So solution series will be homework for you. Now Rodriguez formula for what? Legendre polynomial. We have to prove this. Pnx equals to 1 by 2 to the power n factorial n times differentiation, okay, of x square minus 1 to the power n. This is the Rodriguez formula. We will try to prove here. Let us consider b equals to what? X square minus 1 to the power n. Now dv dx, taking differentiation of b with respect to x, okay, on both sides, n into x square minus n minus 1, again differentiation of x, again differentiation what will be? Twice x. Okay, now multiplying both sides by x square minus 1, we get x square minus 1 into dv dx twice n x square minus 1 whole to the power n. And this is also what? This is the what? B. B equal to what was? X square minus 1 to the power n. So 2n bx. This is the equation number 2. Now by Leibniz theorem, differentiating this equation 2 up to n plus 1 times. Okay, you must know about this Leibniz theorem, n times differentiation formula. In first semester you have done this. Differentiating on both sides n plus 1 times. So x square minus 1, this will be what? N plus 1 times differentiation, what was? D n plus 2 divided by dx n plus 2, and nc1. n c 1. N means what? N plus 1 c 1. And differentiation of this what will be? X square minus 1 differentiation what? Twice x. And this will be reduced 1 dn plus 1 dx minus 1 of b. Okay. Again n plus c 2. Differentiation of twice x what will be? 2. And this will be reduced to 1 dn dxn equal to twice n. This is the actually UV method. X into dn plus 1 and times differentiation n plus 1 times differentiation dn plus 1 dx plus 1 and n plus c nc 1 n means what? N plus 1. The differentiation of x what? 1. And it will be reduced to 1 times. So d to the power n b dxn. Okay. So nc1 formula what? N. nc1 formula what? N. This is the same nc1 formula. And this is the twice x, this is twice x, nc1 minus nc2. Okay. This and this taking common. Okay. This and this taking common, we get this. And this taking common. Okay. Now x square minus 1 dn plus 2 n plus 2 times differentiation twice x. nc1 means n plus nc1 formula what? N. That means this give what? N plus 1. N plus 1 minus n what? Only twice x. So this will n plus nc2 formula what? N into n plus 1 divided by factorial 2. So this will give n into n plus 1 after combination formula. So if we put the n times differentiation of b dxn equals to y, then we can write this differentiation what? D square y by dx square dy dx after putting y equals to this. We get this is the actual differential equation of Legendre differential equation. So this is the solution of Legendre differential equation. Okay. So this can be written as c dvn equal to pnx. Pnx are the Legendre polynomial. Where c is a constant, b because b equals to what was? X square minus 1 to the power n, and this can be written as a plus b into m minus b. Okay. So n times differentiation of b what will be? UB method, n plus 1 into n times differentiation of b and c1, this differentiation. Okay. 1 will be reduced, then this up to dot dot x minus 1, then b, this into n times differentiation of u. Okay. N times differentiation of u equals to 0. Now putting x equals to 1, we get n times differentiation what was? 2 to the power n into n factorial. From this whole series, all will be vanished for x equals to 1 except this. So all the other terms disappear as x minus 1 is a factor in every term except first term only. So this can be written as this whole series c into 2 to the power n into n pn 1. First polynomial, first Legendre function is 1. Pn 1 equals to 1. So c equals to, you can write 1 divided by 2 to the power n factorial. Now substituting these values, substituting where? This values, we get pn equals to nx equals to 1 by 2 to the power n factorial dn db. And this is the Rodriguez formula. B equals to what was? X square minus 1. Okay, practice it at home. I hope everybody can do this. Now example 1, show that minus 1 to plus 1 pn dx equals to 0 for n is not equal to 0, and minus 1 to plus 1 pn x will be 2 for n equals to 0. Actually, we know that pnx equals to what? This is from Rodriguez formula. Rodriguez formula we have proved. Okay, this is the Rodriguez formula for Legendre functions. Remember it. Rodriguez formula for Legendre function. Now integrating, we get minus 1 to 1 pnx dx equals to what will be? Just 1 by twice n factorial minus 1 to plus 1 integration limit, integral limit, lower limit minus 1, dn dxn will be what? This. Now if we take integration within limits minus 1 and plus 1, we get what? 1 will be reduced, 1 differentiation will be, because this is the antiderivatives. So dn minus 1 dxn minus 1. Okay, and limit will be what? Minus 1 to 1. If we put x equals to 1 here, this will be 0, and if we put x equals to minus 1 also, this will become what? 0. That means First differentiation will be what? 0. Understand everybody? Now if we put n equals to 0 here in this Rodriguez formula, 1 by 2 to the power 0, 0 factorial, and this is the 0 times differentiation. This is the to the power 0. This is this to the power 0 what? 1. Okay. So 0 times differentiation will be also 1 because this is the constant. 0 times differentiation can only 1. Okay. So this will be what? 2 to the power 0 means 1. That means only P0x. P0x means what? N equals to 0 in Legendre polynomial. So this is only 1. And 1 integration what x? If we put the upper limit and lower limit, we get only 2. This is actually very easy maths. Now this is the Rodriguez formula. We have proved Pnx equals to what? 1 by 2 to the power n and factorial n times differentiation of x square minus 1 to the power n. If we put n equals to 0, P0x equals to what? 1. If we put n equals to 1, then P1x equals what will be? 1 by 2 to the power 1 and factorial ddx of x square minus 1. Okay. This differentiation what? Only twice x. Just x. That means P1x equals to what? X. If n equals to 2, P2x equals to just putting n equals to 2 here. 1 by 2 square, 2 factorial, and 2 times differentiation, then second derivatives of x square minus 1 whole square. This a minus b whole square formula, and after taking differentiation, we get this. X to the n formula what? N into x to the n minus 1. Okay. So again differentiation of x, twice x. So we get only 1/2 3x square minus 1. Similarly, P3, P4, P5, P6, etc. and Pn we get. Okay. So this is the actually geometrical interpretation of Legendre polynomials, and P0 equals to 1. Okay. This is the actually parallel line with what? X-axis. And P equals and if n equals to 1, P1x equals to what? Only x. This is the actually straight line passing through origin. Okay. Making equal angle with x-axis and y-axis. Okay. This is the x, y equal to x, y equal to x, and slope is 45 degree. So n equals to 2, P2 will be what? This function, y equals to this function. Then you can plot this P2. This is the P2 function. Okay. And P2 function, and P3 where? P3 is the P3 equal to this, y equals to this function can be plotted like this. Okay. You can use different types of software to plot this. P4 will be this. Okay. Y equal to this function. Actually, this is the geometrical interpretation for first 4 polynomials of Legendre. Understand? This is very important for you. Now express this in terms of Legendre polynomials. We have to express this in terms of what? Legendre polynomials. 4x cube plus 6x square 7x plus 2. This is a given function. And this can be written as a into P3 for x cube, and x square P2, and 7 c into P1x, 2 into P0x. Okay, because there is a variable, no variables. This is why P0 polynomial. So we can take this equivalent, and we have to find out a, b, c. P3 what? This. And P2 what? This. P1 equals to x, and P0x equals to 1. 1 from this. Okay. You have to remember this. Just putting values, we get this, and equating from both sides. X cube coefficient what? 1. Same. X cube coefficient here 5a by 2, and x cube coefficient 4. So a equals to what? This. And second term, x square coefficient this equals to 6. Okay, b equals to this. Then x coefficient and x coefficient equals to 7. Just solving, we get this. Okay, very important for you. And similarly, you can solve example 4. This is homework for you. And so this is the actually generating function. 1 minus twice x plus z squared to the power half equals to 1 minus twice x z plus z squared to the power minus half is the ascending power of x. This is the actually Legendre generative function of Legendre polynomial. No need to learn this. Now prove that Pn1 equals to what? 1 using Legendre, generating function for Legendre polynomial. Okay, this is the generating function. Remember it. This is used as using as formula, expressing this in series. Okay, 1 plus x to the power n formula. 1 plus x to the power n formula. Now substituting n equals to 1 for x equals to 1, putting here, we get this is a series, and this series equals to this. So equating the coefficient of z to the power n, z to the power 1, n equals to 1, here coefficient, and here coefficient 1. So Pn1. So Pn1 equals to 1. Try it at home, okay? Example 6. Neat. Now, this is very important, orthogonality of Legendre polynomials. That means minus 1 to the power plus 1 Pm x Pnx equals to 0, where nr and m are not equal. So from Pnx of the solution of Legendre differential equation, and Pm is also the solution of Legendre differential equation of this. Here n and here m. So multiplying equation 1 by z and equation 2 by y. Okay, equation 1 by what? Z, and equation 2 by what? Y. Then this will then subtracting this will be what? Cancelled. Okay, so 1 minus x square will be common to this, and this is the middle term, and this is the twice x term, and this is the last term common with yz. So now integrating from minus 1 to 1, this we have to integrate minus 1 to 1. Integrating, just differentiation will be cancelled. Okay, just putting this whole, taking this whole, because ddx if you take antiderivatives, then it will be cancelled. Just then you can take limit will be what? Lower limit minus 1, upper limit plus 1, and this is integration. This is the whole constant integration of what? Yz. So after putting x equals to minus 1 and plus 1, this will give what? 0. So this is the constant term. This constant term yz equals to 0, and minus 1 plus 1 pmx equals to 0 if n m not equal. Okay, y equals to pnx and z equals to pmx. Putting, very easy for you. I hope everybody can do this. First 1 2 3 4, these 4 relations important for you. Actually I am discussing the first relation. We know that 1 minus twice x z plus z square to the power minus half summation z to the power n pnx. This is the actually generating function for polynomial, Legendre polynomial. Okay, this will be the formula of what? Generating function of Legendre polynomial. Now differentiating with respect to z, we get from both sets. X to the n formula what will be? N into x to the n minus 1. Again differentiation of x minus twice x, another will be constant with respect to z, remember it. So 1 will be 0 and this will be x, and this n into x to the n minus 1. Now multiplying both sides by this, we get this to the power minus 3 by 2 plus 1 means what? Minus half. So this will be after taking common minus 2, we get x minus z. 2 cancel, so we get this, and this equals to this. This is the actually pn summation z to the power n pnx, because this is okay, equation 1. Now equating the coefficient of z to the power n on both sides, z to the power n on both sides of 1, x to the power pnx, x pnx, and pn minus 1x, z reduced 1. Okay, so this is the actually in right hand side we get n plus 1 Pn plus 1 x minus twice x Pn x and minus 1 Pn x. So this is the actually recurrence relation after rearranging.